everyone. This is a continuation of the 7.4, 7.5 worksheet. So you'll see here we have the sine and the cosine function again, and we have a lot of the same variables, the amplitude, the period, and the midline. Those have not changed. The one new thing is the h, which is going to be the horizontal shift. Notice the location of it. It is with the input, so the input is our t value. And then the h is subtracted from that. So the horizontal shift, also sometimes called the phase shift, I'm going to write that on here, phase shift. And what that does is it moves the graph left or right. And it's always going to be the opposite of your intuition. So for example, if we have sine of t plus pi, that means it's going to shift left pi. And if we have sine of t minus pi, that means it's going to shift to the right pi. So that's what the h does. It's that horizontal shift. You also may notice that from the previous section, we had b times t. And notice here that the b has been factored out. So if you ever see something like 3t plus pi, we want to make sure that let me put a sign in front real quick. We want to make sure we factor that 3 out, and then we write it as t plus pi over 3. And so then that tells us it's going to shift left pi over 3 units. For the simplicity of this class, I try not to use both the b and the h in the same problem because that does take some practice in how to deal with both of those things. With our horizontal, the b gives us that horizontal stretch and compression, and then the h gives us the movement left or right. So I just want you to be aware that the b should be factored out. All right, let's go ahead and look at problem number 4. Okay, so here we have, suppose the functions f and g are defined such that f of theta is equal to sine, so that's going to be our original function. And then g of theta is going to be sine of theta plus pi over 2. So based on our conversation just a few seconds ago, you may already identify how this is going to shift. So we know it's going to be opposite of that sine, so it's going to be left pi over 2. And so what I want to do for this problem, even though we already know how it's going to move, I want you to understand why it's actually moving that particular direction. Okay, so what we're going to do is create a table of values for the two functions and then plot the graphs, and then we will see that it actually does shift left pi over 2. All right, so I'm first going to do the column of f of theta, and I'm going to use the trig wheel to help us understand those values. Okay, let's go ahead and start at degree 0, so that is our 3 o'clock position on the wheel. And so we're starting at the 3 o'clock position. Remember, we are looking at the sine of both of these functions, which means we're looking at the vertical distance. So right now, it is on the horizontal diameter, so it's 0 units above and below. If we go to pi over 2, that's that 90 degree or the 12 o'clock position. That puts us 1 unit above. Pi is our 9 o'clock position, and we are right on the horizontal line. 3 pi over 2 brings us to the 6 o'clock position, so we are 1 unit below. 2 pi is back at that 3 o'clock position, and so we are right back on the horizontal line, and then we can keep going around in the circle, so the next one is 1 unit above. All right. Let's look at these first 3 rows. I'm going to start with the negative pi over 2. So that means that we are going in a clockwise direction, right? So all these other ones we were going in a counterclockwise direction, but when we have a negative angle, that is clockwise. So we're going clockwise 90 degrees, or pi over 2, which means we are 1 unit below the horizontal line. Negative pi, or negative 180 degrees, brings us to our 9 o'clock position, which means we are at 0. And this brings us all the way to our 12 o'clock position, which means we are 1 unit above. Okay, let's go ahead and plot those points right away. So we've got pi over 2, pi, 3 pi over 2, 2 pi, and then 5 pi over 2. And then backwards, we've got negative pi over 2, negative pi, and negative 3 pi over 2. Okay, and then we're just going to be 1 unit above and below. So I'm just going to go ahead and use this first tick mark as a positive 1, and there's negative 1. Okay, let's plot these points. Going backwards, we're negative 1. Okay, and then we're going to go ahead and connect the dots here. Okay, so that is our original sine function. Okay, so now let's go ahead and look at sine of theta plus pi over 2. So what we're going to do is I'll plug in the theta value, and then we'll reason through what's happening with our function and then fill in our table. Again, we're going to start with our 0 degrees. So this means that our input is going to be 0. So then we write our equation as sine of 0 plus pi over 2, which means that we are starting at the 0 degrees, but then we're adding the 90 degrees before we evaluate the function. Okay, so if we look at our trig wheel here, we're at 0 degrees. We're going to add pi over 2 and then take the sine of it, meaning we're going to look at the vertical distance there. So the vertical distance here is going to be 1. Okay, the next one, we have pi over 2, so that becomes sine of pi over 2 plus pi over 2, which means we start at the 12 o'clock position, and then we add an additional 90 degrees, which means that this is technically now sine of pi. And then sine of pi means we are at the horizontal line, so we are at 0. Next one is sine of pi plus pi over 2. So visually, we start at our 9 o'clock position, and then we add 90 degrees, which puts us to our which puts us at our 6 o'clock position, which means that once we evaluate the vertical distance, we are now 1 unit below. And so we keep doing that through all of these angle measures. So I will let you go ahead and do that on your own. So go ahead and pause the video while you do the last 3 rows. And so here I've got the last 3 rows. Those solutions are showing on the screen. Okay, and then a very similar thing, but I wanted to show you the visual if we are going in the clockwise direction. So we'll start with the negative pi over 2, so that gives us sine of negative pi over 2 plus pi over 2. So what that means visually is that we are going to be starting at negative pi over 2, so that's at that 6 o'clock position. We are going to add the 90 degrees, which means we are back at this horizontal line. So that means we have a 0. And then a very similar story for all of these other ones, negative pi plus pi over 2. So that means we start at the 9 o'clock position, and then we move counterclockwise 90 degrees. So that gives us the negative 1. And then very similar for that very first one, we're going to be starting at, let me actually just write this out. So when we go negative pi over 2, that means we are going clockwise all the way, so we can think about it going clockwise 270 degrees, which brings us to the 12 o'clock position. And then we move our wheel 90 degrees, which puts us at the 9 o'clock position for a vertical height of 0. So I'm just going to go ahead and erase all of these so we have room on our graph. Okay, and then let's go ahead and plot all of these points. So at negative 3 pi over 2, we are at 0. At negative pi over 2, we're at negative 1. Negative pi over 2, we're at 0, etc. So go ahead and keep plotting all of those points. And then we can connect the dots. And you can see that every single one of these points has shifted to the left pi over 2. Okay, and so that is our phase shift. So that means we are shifting to the left pi over 2. Okay, on problem number 5, it says, what general statement can you make about how the graph of m of theta is equal to cosine theta minus pi compares to the graph of just our cosine theta? So here we're not graphing it. We can just look at this, and we know that it is going to move opposite of that sign, which means it's going to move to the right pi units. All right, number 6, so let's combine a couple things. So we've got 3 sine of theta plus pi, close parentheses, minus 1. So this 3 is our amplitude. This negative 1 is our midline. And then this plus pi means that it's going to move to the left pi units. Okay, so as we start to think about what this graph is going to look like, we know that it's going to be stretched by a factor of 3 because our amplitude is 3. And then this midline is going to be shifted down 1 unit. So typically, I'm just going to draw a little ghost graph over here on the left side. So typically our function, our basic sine function, oscillates between -1 and +1. But with this amplitude of 3, that now means it's going to go up to 3 and down to -3. So again, I'm just going to draw a little quick ghost graph of that. So it does that. And then the midline is going to shift down 1. So I'm going to change colors here. So all of these points are going to shift down 1. So before, it was oscillating between +3 and -3. But because we're shifting it down 1, that means it's now, I'm going to shift each of those down 1, it's now going to be oscillating between a +2 and a -4. So both of these are going to be the max and the mins on our graph. Okay, so I'm going to come over here. We've got these tick marks because of where it needs to go. I'm going to label this first one 2, this one 4, and this one -2 and -4. So that way we have our minimum of -4, and then our 2 is showing up. Okay, so that kind of takes care of our amplitude and our midline, and then we know that it's going to shift left pi over 2. So, okay, so then we also know that our midline has been shifted down 1, so I'm going to draw this midline right through here. And so that means that our function is going to be oscillating around this midline. Okay, so what I'm going to do is just draw a quick rough sketch of our typical sine function before we deal with the left pi over 2. So we start here, we go up 2 units, back to the horizontal line. Here we're at -4, and then we're back. Okay, so we want to think about this midline as like our new x-axis, because that x-axis has been shifted down 1 unit. I'm going to go ahead and just draw this in blue. So this function right here only deals with our amplitude and our midline. Right, so we stretched it by a factor of 3 and then shifted it down 1. Once we have this graph, then we can go ahead and shift everything left pi. So here is -pi over 2. Here is -pi. Let me plot some of these other ones here. Pi over 2, pi, Okay, so we're going to take all of those key points and we're going to shift it left pi. And so we can think about it as we're shifting it left 2 tick marks. That's an easy way to think about the shifting, is how many tick marks. So this very first point that we have, we're going to shift that left 2 units. So that means our new point is going to be right here. This peak where the output is at 2, we're going to shift that left 2 tick marks. So that new point is going to be right here. This blue point at pi, we're going to shift that left 2 tick marks. The valley of -4, shift that left 2 tick marks. And then at 2 pi, we also shift that left 2 tick marks. Okay, we can now connect the dots using our sine function. And that right there is the graph of g of theta. Okay, and then here it says describe how the graph of g compares to the original sine function, and we listed all of those right here. So that 3 is our amplitude, so that vertically stretches our graph. The pi, because it's with the input, that means it's going to be shifting left pi, and then the -1 on the outside represents that we're shifting the midline down 1 unit. All right, and then we have one more graph here, so we want to construct the graph of h given this particular function, and then how do the two compare. So notice that the 3 and the 1 I kept the same, just so you could see that that doesn't change. So the 3 is still our amplitude, the -1 is still going to be our midline, which just like before, it is going to oscillate between 2 and -4, so that same discussion. Okay, and notice here that the 2 is multiplied by our input value. It's multiplied by the theta, which means that it's going to either be a horizontal stretch or a horizontal compression. So let's write that. Okay, so to determine which one, we want to think about that 2 like speed. So that means that we are going twice the speed. And so since we are going faster, that means it's going to take less time to complete the cycle, right? So again, if we're going faster, it takes less time, which then means we have a horizontal compression. Okay, so compression means that it's shorter time, so that means that the input is going to be compressed. So let's look at how this shows up on our graph. Okay, again, I'm going to draw that typical ghost graph just so we can see. I'm going to put in that midline. We still have our generic sine function, so I'm going to go back and put in these values. Okay, so this right here is our general sine function with the amplitude of 3 and the midline of -1. Okay, so now let's look at how this 2 affects the graph. We already talked about that it's going to be a horizontal compression. So if we think about our formula, we have 2 pi over b is the way that we think about our horizontal stretch and compression. So in this case, we have 2 pi over our b is going to be 2. When we simplify that, we get pi, which means that when we are thinking about our horizontal compression, it is going to take pi to complete one cycle. Okay, so right now, if you look at this orange part of the graph, the full cycle is 2 pi. We are going to compress that into completing that same full cycle by the time we reach pi. So when we go to graph this function, we know that it's going to complete one full cycle in pi. And so a way to reason through how to plot these points is that when we were going twice the speed, we know it's taking the reciprocal of that, so it's going to be half of the time. So twice the speed is 2, the reciprocal of that is 1/2. So when we come over here to our graph, we want to think about each of these points as a distance from the y-axis. So at this pi over 2 point, we want to be half of the distance, right? So we can think about that pi over 2 tick mark. We're going to create a tick mark half of that distance and create a new point right there. Okay, let's go to the point at pi. Again, we want half of the distance, so we can think about it as there are 2 tick marks to get to pi. So 1, 2, we want half of that distance. So that is going to be a new point. I'm going to make these points bigger. Okay, the 3 pi over 2, we want half of that distance. So right now we can think about it as 3 tick marks away from our y-axis. We want 1.5 of those. So that's going to be about right here. So that's between tick marks 1 and 2. And that means that that point is going to be down here. And then this last point at 2 pi, right now it's 4 tick marks away. We want half of that distance, which means we want it to be 2 tick marks away. So 1, 2 tick marks. Okay, and then we connect those dots. And that right there gives us our function that is stretched by a factor of 3, shifted down 1, and it is horizontally compressed by 1/2. All right, so big ideas from this section. So we've got our generic function a times f is just our generic name for the function, times b times x minus h plus k. And the a gives us the vertical stretch or compression. In trig, we refer to that as the amplitude. I'm going to jump over to k. So k is the vertical shift, which in trig refers to the midline. Notice that both the a and the k are outside of the function, which means that is affecting things vertically. So it's either a vertical stretch and compression or a vertical shift. Okay, if we go inside the function, so that's the b and the h, both of those are doing things horizontally. So the b is a horizontal stretch or compression. In trig, we refer to that as the period. And then the h is the horizontal shift. In trig, we refer to that as the phase shift. Okay, the other thing I also want to point out is that when the variable is multiplied, that's the stretch and compression, right? So notice the a is multiplied by the function, the b is multiplied by the input. So when it's multiplied, that's the stretch and compression. And then for the h and k, notice both of those are either added or subtracted. So when that happens, that is going to give us a shift, right? So outside the function gives us the vertical shift, inside the function gives us the horizontal shift. All right, and then the last thing to really make sure you are mindful of is that when we think about the relationship that the period is equal to 2 pi over b, remember that the period is how long it takes to complete one cycle, and the b represents the value in the equation, right? So if you have a graph, that's indicating the period. If you have the equation, that is giving you the b value. All right, that is it for this worksheet. See you in the next video.